love when that works. Every time, as always. Alrighty, folks. It is Monday. Happy Monday. We got a couple of things today. We have Prime Mystery Wednesday. Worked out well. We were able to be a little bit ahead. I don't think we're behind. Music. There we go. So we're going to move on to recursion. Right, we talked about our ADT, our containers. Hopefully lab was interesting is the right word. Having a chance to practice with them, if nothing else, right? Using containers or containers of containers, this sort of combination is lots of fun. So recursion is something you should have heard about, I hope, last semester or whenever you took 150, but probably didn't spend a lot of time on. Is that correct? Okay. I don't want to spend too much time going over stuff you already did. But we're going to go deeper into recursion here and have a little bit of fun with it, if that makes any sense. So we start up a new project. Oh, no, before that, that's right. I want to talk about project one. I got a bunch of good questions because you watched me write this and it was a bit nonsense. I apologize. So most questions here around character for weapon is a pointer. And when you use a pointer for weapon, that way we can get the virtual functions working. Right? If we don't have a pointer for it, it's not going to work very well for us to get those virtual functions working. Okay. So if we don't have a weapon, we're going to use this null pointer thing. I think I skipped over most of this. So null pointer is a pointer that points to nothing or null. So that's a particular kind of pointer. Let me start a new project here real quick. Did I do week numbers? I can never remember. Is this week 7? Topic, just the topic, recursion. So a pointer that doesn't reference anything. What you want to reference specifically is a special keyword called a null pointer. So that way you can check for you don't point anywhere. And that's our goal here. So if I want a pointer, space, stream, strings. Hector, my friend, thank you so much for donating to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. You're a legend. All right, so if I had, say, a integer pointer for number, right, I can assign number the value of null PTR. Null PTR or null pointer, I don't know why we bother abbreviating these things. It's not that much harder to type a couple more letters, but we do, is a specific value of nothing. So if we go and look at this, if I go and see out number now, probably an end line, and put this in debug mode. So we're going to hit our breakpoint here, and it should pause. And so right now, we're about to assign number a value, right? We've told C++ I want a pointer for number. Doesn't reserve any memory yet, right? I've got a variable. There is no value yet. Once I go and give it a value, now, it didn't update. It should set it to 0. It's essentially 0. So it's like the memory address is 0. Otherwise, you can end up at weird spaces of memory here. So if I go and see out this, where's my value here? We get 0. The memory address is literally 0. Right? So if you try and read the memory at 0, it's not going to work very well for you. Bad stuff will happen. Right? There's probably garbage there anyway. Right? Of all the billions of bytes of memory we have, nothing at 0. Okay. So the null pointer then is that special address to say I don't point anywhere. I don't have a value. So we can check for that. We can say, hey, if number is equal to a null pointer, then we can do something. See out, enter a value. And then we can see in a value for number. Well, not for number directly, right, because it's a pointer to the dereferenced location. We can see in a value, right? And see, now it will give it a value. Right? It is nothing, points nowhere. So my if is true, right? I have no value. All right, so we can go ask for value. Go get, I don't know, 42. Oh, I got to run this line, sorry. Now I can probably type in here. Can't type. Uh-oh, we broke it. It's our exception. Access violation, reading location 0. Well, if we point to 0, I can't stick a value in 0, right? This is no good. I've set the pointer to nowhere, and I try and go put a value there, it's going to crash on me. Can't read it there, right? So I need to see in a different value, and then I can go assign it a value, right? Because I'm dealing with pointers. Pointers are fun like that. So if we want an int for other number, then I can see an other number. Then I can assign my number pointer to the other number. Enter value, 2. Oh, it's already yelling at me here. What's it yelling about? Still can't write to null. Nope, can't assign it to this value. Right? We can say the pointer will point to a new location, but if I try and dereference something that points to nothing, it's going to crash every time. Right? So if I'm pointing at null pointer, you can't dereference this. We can't use it. What I want to do then is assign it the value of the reference of another number. Right? The other number is somewhere out in memory. I want its address to now be stored in this pointer instead of null pointer. Right? So we should put in some notes here. So can't dereference pointer pointing to null pointer. Right? And leave that commented out, right? Number equals something. Right? This is no good. But we can change the value stored by the pointer to be a valid memory location. That's the idea. So it gets a little funny here, but we need to be checking, right? If we don't point to anything, now I can go do something with it. If I do point to something else, else, great. We'll say, I don't know, it doesn't have a value right now, but or has a value, which it doesn't, but that's okay. So now this one should work, and we should be able to point at that particular value. All right, so enter a number, say, come on, 42. So now we have number, still has nothing right now, right? It's a pointer, it points to no memory address. We're about to assign the value of the pointer, which is a memory address, to the address of another number. Wherever that got stored in memory, now we have a valid pointer, right? If we're not null pointer, I'm pointing somewhere in memory, and I can probably go use this thing. It gets a little funny here, trying to deal with all these pointers. So, but if we don't have a value, it can be null, right? If we don't give it null and we don't have a value, there's not really a good way of knowing if we don't have a value or not. Right? Without using this null pointer, how would I know if number had a valid value? Right? We could look at the value that it stores, maybe, but there's always going to be something at the memory address where it points if it's not this null pointer. I should have put this in a different class here. Let me rename this one here. This is pointers and null PTR. Okay, sure. I'm just going to leave this in that project if that's okay. And then we'll go back to recursion here. All right, so that's the null pointer weapon thing. So if we don't have a weapon, it's null pointer. We can say our range is square root of 2. Still, if we hit this roll a 20-sided die, is determining whether or not we hit the target, and then the attack does 1 damage. With that attack function, you're accepting another character to attack, right? The person who takes the damage is not you. It's not the this, it's the character reference you passed, right? I have a character, I'm calling the function attack on this character, giving it a character over here to attack. The character you're attacking is the one that takes the damage, right? So we got to be careful when we're calling our functions, we're making sure the right reference is being used, right? The this is the current character that you called the function on. The character reference that you have in the function is who you're attacking, the target. So we're dealing with two different characters here as we work with this. And then some other questions. We're just writing the classes here, right? Nothing has to be in main, although I would recommend you do some sort of testing. I prefer unit tests because I think they're easier to write than a main method that has a bunch of C-ins and C-outs, but that's just me and I've done them a bunch. You know, any code you write is worth testing. I'm not giving you points for the testing though. Right? The points come from do they do the right things here. So do you have your character class? Does it do the right things? Do you have the magic character subclass? Does it do the right things? The weapon class and the healing stick subclass. I have terrible names for things. I'm sorry. I reuse myself sometimes. You had a Toucan. You had a problem with the reference to character. If you're passing a copy. Yeah, if you don't pass the reference to it, you can get a copy of it, right? If we're not careful. So when you have the target here, and you say, hey, give me a character reference to target, we don't want a default copy to happen. Right? We want to actually give the reference to where that is in memory so we can affect it with like a take damage function and it would stay affected. Yeah, it's a good catch, Toucan. And that's the kind of thing you're not going to see unless you actually do some testing. It just won't. You think it might work, but you know we'll have to find out after. All right, other questions? Yeah.
So if the character has 0 hit points, nothing happens.
So if you try an attack and the character that you're attacking with has 0 hit points, just no op, just do nothing. Yeah, like at 0 hit points, the characters are considered either dead or unconscious, depending on what kind of game you play. So you can't attack. But because the class has a function for attack, you can call attack no matter what, even if the character's dead. So the code then will make sure dead characters don't move, essentially. Does that make sense? Okay, so if you're trying the attack function and you have 0 hit points, just skip everything else. Just don't do anything. Yeah.
You weapon equals no pointer, then can you still assign a weapon on the weapon class if the range is square root? Can you still assign that stuff?
So if you have a null pointer, you can't call functions, right? If you tried like and said, hey, this pointer and the arrow notation to call a function, it's going to crash on you because it points nowhere and you can't access anything at 0 memory. So you don't need to do any set range. You just say, hey, I know what my range is. I don't need to go get the range from the weapon because there is no weapon. I'll just.
So I don't have to call the range is.
Yeah. So if you don't have a weapon, your range is square root of 2. Yeah. Yeah. So some people had some questions about the range of weapons. Probably a double, right? If we're dealing with square root of 2 or other sorts of interesting values here, probably want it to be a double. I mean, it'll work either way, but double is probably a more appropriate value there. And then if you're within range is less than or equal to, right? You can be equal to the square root of 2, but if you're checking only specifically less than, you're never going to be able to hit anyone, like unless they're at the same location as you. So check your less than and equal to's on those. All right, I think that's it for questions. Anyone else have other questions? All right, one more reminder, the due date for this, 11 a.m., right? We're going over the solution in class. I don't know how many emails I got on Project Zero, and that's okay, mistakes happen. It's not the end of the world, where people said, oh, I thought it wasn't due till the night, despite me saying it every time, right? I'm going over the solution in class. So I'm preaching to the choir here because you guys actually show up and listen, so I apologize. For anyone on the recording, do it 11. Yeah. All right, so we're going to move on to recursion, right? Let me go grab some of this stuff real quick. And grab that too. Should probably return a 0. That's probably more proper, right? To eventually return a 0 on main. So with recursion, right, our definition is a function that calls itself, right? So if we have a, I don't know, a void function, countdown, this is the silly one, int value, right? We can see out the value and then we'll call countdown again with value minus minus if we're not at the end, right? With a recursive anything, you need to identify two things. If you don't identify these two things, don't use recursion, right? The first one is, do I have what we'll call a base case? Do I have a simple solution? Do I know when I'm done, right? Okay, well, countdown is done, we'll say when we get to 0. So if value does not equal 0, let's go. So the first one here, right, this is our base case. Value is 0. If value is 0, we're done. We've solved the problem. Again, countdown is not really a problem we're solving, but it's a quick example here. Right, so I know when to stop. The other thing we have to be able to identify is, can I take a problem that is not solved and make it one step closer to being solved? Right? Can I take a complex case that is your complex if it's not solved, and make it approach the base case, the one where I know a solution? Those two things. Right? If we can do those two things, you might be able to solve the problem with recursion. If you can't do those two things, you can't solve the problem with recursion. It's a really good rule. Okay? So if you can do both, maybe. If you can't do both, no. And that's our rule of thumb for this. So great. Our one step, we'll do something, and then we'll see, are we at the base case? No? All right, let's make it simpler. By making it simpler, we'll decrease the value by 1. Right? So I can count down from 10. Did I add an end lines? I think I added end lines. Uh-oh. Oh, too many mains. Shoot. All right, forget you. That's annoying. I'll come back here, and we'll put this in later. I should just move it to the other project. I'm sorry. Uh-oh. 10. We're at 10. It crashed. Why is this not? Why did I stay at 10? What does this decrement increment, this operator do? It uses the value and then it subtracts 1. This is that fun case where if you do the pre-decrement, you subtract 1 from the value, then you use the value, life might be better for you, right? Now let's try it. Do I count down? Blast off. Anyone watch the rocket launch? People still watch those? I think they're cool. I'm scared to have my kids watch them though in case they blow up. I'll be honest. Oh, yeah, I don't know. Is it going to mess them up if they watch that live? Maybe. I mean, they're going to be messed up anyway. They're my kids, but I don't know. Okay. So countdown. This is decent here. Now, it still has problems, right? Anyone think of a quick problem with this one? Yeah. Yeah, a negative value. If I give it negative 10, I will count down until I crash. There it goes. Uh-oh. Stack Overflow. This is why the website's named Stack Overflow, right? It's a common exception. So the stack of memory only has so much space. If you run out of space, you've overflowed your stack. Stack Overflow. Ha, ha, ha. We learned a thing today. Did you already see this 150? No. Good. Yes, something new. I don't know. I like new stuff. New stuff is much more fun, for sure. So this is another reason the heap and dynamic memory is good. You have a lot more space out in the heap. If you overflow the heap, bad stuff happens. Generally, like your computer will be very upset with you if you take up all the memory. Yeah.
Would you say using recursion is more efficient or less efficient than using a function?
So recursion is by definition less efficient. It's easier for certain types of problems though, where doing a non-recursive solution is just hard. And there's lots of cases where that's true. So recursion is a simple way to approach a lot of problems. It just works easily. We'll look at a couple different ones about that as well. Yeah, so anything you can solve with recursion can be solved without recursion. But the flip is not true, right? If you can't identify those two things, you can't solve it with recursion. So just because you can solve it, we'll call that like iteratively, doesn't mean you can solve it with recursion. So yeah, countdown is silly. It doesn't need to be a recursive solution. It could just be a function, right? Countdown without recursion, int value, right? We don't even need to, we're printing out the value and then we're checking if it's not 0. We could say while it's not 0, right? See out. Right? We've done the same thing now without recursion, right? It's just a loop. So simple recursion that's just a loop, not very interesting, right? But that's the simple one to talk about here, for sure. So this is, you don't need to know, right? That this title is self-explanatory enough. Okay. So yeah, negative is an issue here. So maybe what we want to do then is say a value is greater than 0. We should keep recursing. This will stop our negative value problem. We're still going to spit out the first number and say, hey, -10, and then we just stop silently. But at least it solves the problem, right? So again, probably with this one as well, while value is greater than 0, go and do something to fix that one as well. Otherwise, you have an infinite loop. So you have to be careful. You don't want infinite loops, right? Those are probably bad. Okay, that's the simple one. Did you guys do Fibonacci in 150? I got 1 yes. Oh, no, okay, we can do it then. So the Fibonacci sequence, it's a famous mathematical sequence, which is super fun. It, by definition, right, if we look up Fibonacci, I can never spell here, Fibonacci sequence. Take a look at the Wikipedia page. This one here. The 0th value in Fibonacci is 0. The first value of the Fibonacci sequence is 1. These are the known cases. Anything other than 0 and 1 is defined as n-1 plus n-2. Notice that's recursive. Hey, we can do recursion now, right? How cool is this? So we can do that as long as n is greater than 1. We can do this recursion stuff, right? So if we want to have a function for fib nth, I'm bad at spelling Fibonacci, and this is the nth value. So if you give me the nth fib value, I'll tell you what the value of Fibonacci is, right? We can say, hey, if nth is equal to 0 or nth is equal to 1, we return, oh, I guess they're both values are different here. So if it's 0, return 0, else if nth is 1, return 1, right? Those are our first two cases. And I'm going to cheat here a little bit and say if we're less than or equal to 0, just to make sure we don't get infinite loops. And say, hey, if you ask for a negative Fibonacci, I'm just going to tell you 0 and make you go away. Because I don't think that you can have negative Fibonacci sequences. Yeah?
Couldn't you get it all in one line by saying return n?
Return n. Yes, but now it doesn't work. It wouldn't work for the negatives. I guess that's fine because I'm going to give you garbage if you give me garbage.
I mean, you still would have done the negative that way, then would have just returned a negative.
Yeah. Yeah, that could be fun. Is one line. I like that. We're following the math definition here maybe a little more closely. I don't know. Sure. If it's not either of those, right? So these are the base cases, right? Base cases. Notice the S here. You can have more than one base case, right? More than one solution that more than one value that has a known solution, right? This idea. If I have a known solution, that's it. It's my base case. I'm done. If it's not the base case, well, how do I solve this? Well, I can return fib nth of nth minus 1 plus fib nth of nth minus 2. That's the mathematical definition. This works in code, right? It will call itself recursively, the value of nth minus 1 plus the value of itself minus nth minus 2 recursively. Sure. So I don't want to count down here. I want to say, how about for int nth is 0, nth is, I don't know, let's go to like 20 values here, nth plus plus. We want to see out fib nth of nth. Right? We'll calculate the first 20, right? See what we get. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. I can't remember it past that. The first couple I got memorized because that's the kind of thing that's in my head. Don't know why. Yeah.
Does the Fibonacci sequence have any programming?
Specifically for programming, I don't think so. It's just a really cool mathematical sequence, right? And this idea with the golden ratio and all sorts of other things. It's fun. So, and when you take discrete 1, 275, you'll probably play with Fibonacci. Probably. I guess depends who teaches it now. I know the previous instructor used to spend time with Fibonacci. That's a good example. It turns out there's actually a non-recursive formula. When I learned that, it blew my mind. Like, there's a way to do it without recursion. That was super cool. And it's not a loop either. Like, it's just a formula. Plug in a value, you get a value back out. But yeah, it's cool. Lots of fun stuff, mostly with math for Fibonacci. But this is a fine basic definition here. It's a terrible definition though, right? So what we can do, let me put a breakpoint here and then, nope, this one, conditions. I want to say if n equals, I will say 10, right? Let's stop at 10. Conditions, add conditions. Only, is that all I need? I think that's it. Let's try that. There we go. Yeah, I don't want to have to click through the other ones. Those conditions are super handy too for these breakpoints. If you haven't played with those before. So I'm in Fibonacci, right? Or fib nth here. Nth is currently 10, right? So if I step into my function now, I'm at fib, nth is 10. We'll keep on going. All right, now fib, I want to step into, here we go. Now nth is 10 again, right? Step in. Nth is now 8, right? This was the nth of -2. Step again. Step again. Notice they keep piling up here. This is the call stack. So we can see in debug mode the list of functions that are waiting to execute. Right? When you call a function, C++ says, okay, this is where I was. I went to this location. Right? I was at line 14. Now I'm at the next line. Now I'm at the next line. Now I'm at the next line. And we can see each one of these. Right? If I want to see what the values were at that time. So this is why the question earlier, is recursion efficient versus a loop? It is less efficient because every time you call a recursive function, C++ has to track this value in the stack. So it's tracking the function, it's tracking all of the values of the variables as well. And this is not a lot, it's a single integer. But if we said like fib of 1,000, I would have more than 1,000, but essentially 1,000 function calls stacked. Right? When nth was 1,000, when nth was 999, 998, 997, 996, on and on and on. So we have to track all of that in memory so that C++ knows where to go back when it's done. So this is a very inefficient function because we're essentially counting down to 1 and adding up 1 that many times. Right? The only value we're ever going to get out is 1. So anytime we call fib of something, it is spawning new calls and new calls and new calls and new calls. And I should have brought I wanted to bring my drawing tablet. That's okay. I can draw with this. So fib of 10, right, spawns 9 and 8. 9 spawns 8 and 7. 8 spawns 7 and 6. 7 spawns 6 and 5. Right? This one over here, 8 does 7 and 6. This 7 does 6 and 5. Right? Do you see the idea of how many times we're going to have to be, for a simple value like 10, how many other calls I have to make to this function? It's factorial, exponential. It's some real bad amount here. I forget the right term here, but it's going to give us this many function calls, right? It's going to be 55 calls just for 10 to get the value 55 back out, because it adds up 55 times. Yeah, I'll just continue here. Continue. right? So this is terribly inefficient. I've added up 4,000, and now it's fast enough, right? Computers are relatively quick. It didn't complain much. But if I go much further here, we say, hey, let's do the first like 35 values of Fibonacci. I think I can do without blowing up. Let's try it. Okay, cool. Yeah, so that's 5 million. Let's go a little higher. Let's do, I think 40 usually crashes. Let's see. Maybe not crashes, this takes a long time. There we go. You can see it's slowing down. We got to 63 million here. Okay, let's go a little higher. Let's do 45. Where'd it go? Come on. Show me the process. Oh, I want to see the window. There it goes. So you see it's taking even more time because it's adding a 1 that many times. So it's a billion function calls, or 100 million function calls, 165 million function calls are happening. 267 million function calls of adding up 1. Now, it's not a lot, so we never overflow the stack. Right? We don't get the stack overflow exception because the most we have at one time is nth. So only 45 at a time, right? Where 45 called 44, which called 43, which called 42, which called 41, on and on and on. And then we come back and get all the -2s. So at a given time, we only have 45 or less in the stack. It's not too many calls in the stack to overflow anything. It's just really slow because we have to do so many stupid operations here. It's terribly inefficient, but it works, right? So that's the problem sometimes that we're going to run into with recursion, is that it might work, but we might do it very badly here with something like this. So a better way of solving Fibonacci here that still uses recursion uses a technique we're gonna call like a private helper function, essentially. So fib of nth is easy. You just tell me the nth value, great, I know what to do. But I can write another Fibonacci one here. So this is, we'll call this better fib nth. Takes an int for nth. It's going to start the same here, where we just check for our base cases. Then what it's going to do, we're going to have a helper function here. So this will be my better fib nth helper. And helper is a terrible name specifically here, but that's okay. So I know the nth. I have an int for current nth. I have an int for previous. I have an int for current. Okay, so I'm going to have a helper function that has additional values here. These additional values will make this a lot easier for me. Here, I can say, hey, if the nth is equal to the current nth, return current. Right? You tell me what the current value is. If you want that current nth, I'll just give it to you. We're done. Otherwise, we're going to say, hey, my int for next is my previous. Oh my goodness. Plus the current, and then I'm going to return my better fib nth helper of still nth is the goal, my current nth plus plus, right? Add 1 to that, right? And then now what is previous is my current value, and what the new current value is the next value. Right? We're going to do that arithmetic like we just did here, and so some people just put that arithmetic right in here. I find that confusing. I don't mind the extra step here to explicitly call out this is what next is, and a semicolon, right? Okay. So then for better fib nth, then we're going to return my better fib nth helper given nth. The current nth now, if we're not 0 or 1, right? Well, where are we? Well, currently I'm at 1, and I know my previous value was 0 and my current value was 1. If we wanted, we could cheat and go over to 2 and say, hey, 1 and 1. That's probably fine as well, right? I know the next value. So if it's not 0, it's not 1. I know the second nth, right? And I know it was 0 and then it's 1 and then it's 1. So the second nth is 1 here, right? So we can do these, and then if instead of fib of nth, if we do the current better fib nth here, essentially this is counting up, right? Instead of adding up a bunch of 1s, we're adding the actual Fibonacci values, right? So if I want the 45th Fibonacci value will essentially have called this 45 times, right? So let me put a breakpoint in here. We can watch some of these run because it's fun. So 0 and 1 are boring, right? We just get solutions. Let's just skip over those ones here. Now 2, let's step into our code here. Now we're better fib of nth, right? Nth is 2, so we're not 0, we're not 1. Let's go to better fib nth helper. So we'll step into this one. Now nth is, there we go. Nth is 2, current nth is 2. So if it's true, we'll return the current. Okay, that one was done, easy. We print that one out. 3, nth of 3. Step, 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 step. Step into our code. Right, nth, target nth is 3, current nth is 2. Do we match? No. Okay, so let's calculate the next. So previous was 1, current was 1. So the next value now is 2. Let's step into the helper. Right, target nth is 3. The current nth is now 3. My previous value was 1. My current value is 2. Right, do we reach the current value? Yes, we did. The target nth. We reach the current nth, return the current. Right, so we just run this. We take out the breakpoint here and continue that. Notice it's done already. Right, there was no waiting. It can do 45 mathematical additions really fast, right? It doesn't need to do 700 million addition operations. So this is better, right? We don't have that many calls recursively happening. Now, and you're probably thinking to yourself, this could just be a loop, and you're right? It doesn't need any of this stuff. So we can have just a fib loop here. So we'll have a int for fib loop, takes an int for nth, right? Easy here. So again, checking for the base cases probably makes a lot of sense here. Otherwise, we'll say, hey, int for current nth is 2, no 1, right? And then we'll have an int for previous is 1. I guess we can start at 2, right? 2, and then int for current is 1. And while current nth does not equal nth, right? If we're not there yet, we'll keep on adding. When we're done, we can return the current value. So int for next is previous plus current. Plus current. Previous is equal to previous. I can't spell here. I'm sorry. Previous is the current. Current is the next. Take current nth plus plus. Right, just a loop. We can do this arithmetic in a loop here. We don't need the recursion. Okay. Making sense so far? All right. So these were what we'll call relatively easy cases. This is essentially just recursion as a loop. You don't really gain a whole lot here using recursion if it's just a loop. So let's look at one that's more fun. All right. Let's look at, say, add a new item here. I'm going to add a class here. Do you guys play Sudoku? Sudoku. All right, well, let's add a Sudoku class here. Sudoku. Did I spell that right? I hope I spelled it right. We'll have private values. We'll have public values. Right. Sudoku is a 9x9 grid with values 1 to 9. Right. If I can pull up a Sudoku puzzle here. That's Wikipedia, right? That one's safe to pull up. So you get a 9x9 grid with the values 1 to 9. And the idea here, it's a puzzle because each row, rows are this direction, come on, rows are this way. Each row and each column have the values 1 through 9 with no repeats. And each 3x3 section inside this has the values 1 to 9 with no repeats. So your unique 1 to 9 in the row, in the column, and in your 3x3 grid, given these 9 grids of 3x3 on the entire board, right? Okay, so that's Sudoku. So we could say that might be a vector of integers. Can we call it that? Right, a two-dimensional vector. So if we have we gotta include all that stuff, right? Using namespace standard, name spect. We want to include vector. So if we have a vector of type integer, this is the board here, right? We can have some values that we can store. Now, I don't want to have to go and set these individually here. I think that's a big pain here. So I'm going to write a constructor, Sudoku constructor, that accepts one of these. Vector of type int is the board. We'll just say my board is your board. Right. So if you give me a board, good, I'm going to go. Okay. Then what we want to do is we want to try and solve Sudoku. We're going to write a solve function here. That's probably make it a void function here. At some point you can have return true or false, and that sort of stuff confuses me sometimes. We'll just have a solve function. Okay. Well, how do we know when Sudoku's solved? What's our base case, right? How do we know when we're solved? Yeah, everything's filled in. Okay, so I can't have no number. So is it okay if we use zeros instead of numbers? If that can be too confusing, we just use zeros. Sure. Okay, so we'll have zeros then instead. So we'll say for we want a vector of type int. We'll call this the row in board here, right? If my row, what is it? Isn't there a contains? Didn't I have a contains here? My goodness, what was that? Plus vector contain. We just did this chapter last week, right? Find, right? My find function, is that it? TechieDelight.com? Sure. The count function, there we go, count. Looking for a count. That's probably easy, right? Do you want to use count or you just want to do it the hard way? Okay, we can use count. All right, thank you. So we need to include algorithm here then, right? So I don't know why I keep going back to Word. Let me just close Word. I think I just want to keep clicking it. So we'll include algorithm. So if our count of, okay, where are we going to start? We're going to start at row.beginning. Where do we want to end? We're going to end at row.end. And then what do we want to find? We want to try and find a 0. If the count of 0 is greater than 0, we return false, right? Oh, there's no, shoot. We'll make that a Boolean function. Why not? We'll return false. That's not even it. Nope. No, this shouldn't even be here. Let's make a helper function here. I don't want to stop. I guess it'll stop here, but no, we don't want it to stop. This is no good. Sorry. Let's put a helper function here. So let's have a Boolean for is solved. Let's do this here. If we find a 0, we're not solved. False. If we've gone through every single row and we haven't found a 0, we're going to return true. Right? So this is a private function. I don't need to give this function to anyone else outside of this class. No one else should have access to using it, knowing whether or not it's solved. Right? We don't need to give them access. So we'll keep it out of the public list here. Well, now we can check. Okay, so if is solved, I don't know, return true. I guess we just stop, right? We'll put this back to void here. So really, we want the opposite, right? If we're not solved, then we need to go do something, right? We have work to do. We haven't reached a base case if we're not solved. Okay, well, what do I want to do? I want to find the first available open spot. So I don't want to change a number that's already there, right? I want to find the first open spot, right? So I need to go find the first 0 spot. Okay, now again, I'm going to put that as another function here because I think that's probably a small problem we could break out and solve separately than everything else. Is that fair? So we'll say, hey, we want a pair of int for get first open location. Right. So this will return the row and column as a pair. So I know what row and I know what column is in a vector of vectors. I have rows and I have columns, right? So I have all these index values here. Okay, so we're going to say for int row index 0, row index is less than. Now I know the max here is 9. I feel a little bad using 9s here, so I'm going to have a constant int for max index just so I have a name here, right? Having numbers without names, we call those magic numbers, generally bad form, right? Because a number without a name, it has no context. So by giving it a name here, we add some context to that value. It doesn't change the code at all, but it's just a little cleaner here. Like row index plus plus. Okay. So I'll come back to this one here. We'll finish this one in a little bit here. But what we want to do, right? We're going to take the pair of int here. This is my open indexes is my find first open index. What is it here? Get first open location. There we go. Right, that's the first location that's open. So what we want to do, then we're going to say for int, and now the values that can go in are 1 to 9. So look for value starting at 1. Value is less than or equal to 9. And maybe again you might want a word here for this one. And we're using the literal number values. I don't feel so strongly about this one having a max number. I don't think they make Sudoku puzzles that go for 9, do they? That'd be crazy. They have like a 16 by 16 with numbers 1 to 16. That might be fun. Maybe they do. I don't know. Are you okay with 9 being here instead of like a max value? Okay. Value plus plus. Now we need to see, can we put a number here? Right? If can place value at the open indexes first, open indexes second, value. Right? If we can put the value in, let's put the value in. So we need a function for can we put the value in, right? This is a step we can do, and humans are pretty good at this, right? I'll say, hey, can I put a number here? Well, what steps do we need to do? Well, I need to see, is it unique in the row? Is it unique in the column? And is it unique in the grid? Right? Humans do that pretty quick. We're not great Sudoku solvers. Computers are better at it, but like the steps here, we kind of just know. It's a little easier for that. So we'll have a function for can place value. So have a Boolean can place value given an int for row index, an int for column index, and an int for the value. Right? So we can place the value if it's unique in the row, unique in the column, and unique in the grid. Right? So we'll return is value unique in row given the row index. Right? If it's unique in the row, and is it unique in the column? Is unique in column given the column index. Right? And is value unique in grid given the row index and the column index. Column index. Right? If all 3 of those are true, then I'll return as true. Again, I don't know how to do these yet, but that's the step we're going to take, right? So we can add some more. So we'll add a function. I think, can I just click here? Is it going to give me that as a create definition? There we go. Did it do it? It did it. Did it do it? It gave it to me. What is it? Come on. Create the definition. I think it's confused. Why is it so confused? All right, it's not working. Sometimes it works for you here. Sorry. Int row index. Right, and then another one for a Boolean here as an int. Right, and one last one here. A Boolean given an int row index and an int column index. Okay, so we're breaking it down step by step by step, right? This is my functional decomposition. That's my favorite party term. Everyone knows I'm weird and a nerd, so like it doesn't surprise them anymore. But throw this out at your Halloween party, right? Be like, man, I was doing so much functional decomposition for school, and just look at everyone's faces. Just be like, what are you talking about, weirdo? It's a good technical term, though. It's good. Just breaking it down step by step by step by step. So if we can place the value there, great, let's do it. Right? We'll take our board, right, at the row index. So row index is going to be my open indexes first, right? At the column index, my open indexes dot second, right? We want to assign it the value of value, right? If we can put it there, let's put it there, right? That's it. What do we do next? We put a value there. What's the next step? So once I put a number in Sudoku, what do I do? Well, we didn't place it if it wasn't unique. So we put a unique value in. What's the next step in trying to solve the puzzle? Are we done? Yeah. Check the next one. So solve, right? Call solve. Get the next open location. Try and put a value in there, right? What happens if we hit a dead end? This is where it gets interesting. This is where recursion is easier than trying to do this iteratively, because honestly, writing this iteratively is a big pain, and I get confused very easily. No, it's okay. This one is a little more doable than some of the other ones we'll look at, but it's still, I think this is a nice, easy example here. So let's try it. I don't actually know how fast we'll get to maybe I should bring the tablet here. Maybe next time I'll bring the tablet. But in our puzzle, right? Can we put a 1 here? This is the first open spot. Can we put a 1 here? The row's clear, the column's clear, the grid's clear. Great, we put a 1. We call solve. Okay, we're on to here now. Can I put a 1 here? No, because there's a 1 in this column. Can I put a 2 here? 2 is clear. Great, we put a 2 in. Go to the next open spot. Can I put a 1 in? No. Can I put a 2 in? No. Can I put a 3 in? No. Can I put a 4 in? Sure. Right, 4 is open. We put a 4 here. Go to the next one. Can I put a 1 in? Yes? No, because there's a 1 over here. That's right. Nope. Can I put a 2? No. Can I put a 3? No. Can I put a 4? No. Can I put a 5? No. Can I put a 6? No. Can I put a 7? No. Can I put an 8? 8 looks okay. We put an 8 in. Go to the next one. Can I do 1 through 8? No. Can I put a 9? Sure, 9 looks fine. Great. Let's go to the next one. Can I put 1 through 9? No. What do we do? What happens? If we can't place anything, well, this call to solve is done. Right? This idea that we have this call stack happening, I can track these here. So we had, right? So we had a 1, right? So we had the row and column essentially, right? So we got to, this was row 0, column 3, right? So we were at 0, 3 essentially, right? 0, 3 was the row column. We put a 1 in. And then we were at 0, 4, right? And we put a 2 in. We got to 0, 6, right? We skipped over 5 because it wasn't open. 0, 6, we put a 4 in, right? We got to 0, 7, and we put a 7 in. No, an 8. We put an 8 in, right? An 8. We got to 0, 8. We put a 9 in. And then we got to 0, 9. And it said, I can't put anything in. So that call to solve here is done. It comes off the call stack, right? We're done with it. We come right back to the call to solve at 0, 8. We just put a 9 in. There's nothing else for it to try, right? Uh-oh. We got to take it off the board, right? We need to undo that step, right? So to undo that step, so if we come back from solve here, right? If we're not solved, we need to undo. So to undo, we take that spot and put a 0 back in, right? This is undo, right? When solve is done, when the recursive call to solve is done, if we didn't finish the puzzle, we put a bad number in, take it out, right? Take out the number. So now 9 is done, right? We took it out, it's gone. We're back to 0, 7. We just put an 8 in here. We said, okay, are we solved? No? Okay, take the 8 out. What's next in the for loop? Well, the for loop said, okay, hey, try a 9. So we'll come back, and in this location then, we're going to try the 9. Is a 9 okay here? Sure, looks okay. Good in the row, good in the column. Now we'll move on. So it'll call recursively then. So now we have 9 instead of 8 here, and we go to 0, 8. And we're going to try putting all the numbers here. Right? Well, I think an 8 fits. Sure. We get to 0, 9. Can we put a number in? Nope, we're done. Game over. That one gets erased. The 8 didn't fit, erase the 8, right? Put the 0 in, and then a 9 doesn't fit, so this one's done. So then 0, 7, we get back to 0, 7, we just put a 9 in, we're not solved, erase it. Take that one out, this call comes off the call stack, now we're back to 0, 6, where we put a 4 in. Erase the 4, we're not solved, try a 5. Right, so at 0, 6, can we try a 5? No. Can we try a 6? Sure, a 6 fits here. Right, and then we'll call solve, we'll be at 0, 7. We'll call solve, right? So this recursive step here just keeps on trying numbers until we find a solution. All right, the other thing we need to be able to do is print the board. I don't usually recommend classes see out things. I'm going to break that rule now because I want to be lazy. We could turn it all into a string. Sure, I think this will be faster. Is that okay? Right, this should return a string instead for classes being classes, right? You want classes to be reusable. I'm just being lazy. Is that okay? Print board. Will someone tell me it's okay? Validate me. Okay, thank you. It's okay. All right. I want you to know it's bad, but we're going to do it anyway because we're lazy and we're running out of time. Okay. So for a vector of int row in the board, we want to print these things, right? We want to print them out. So we'll see out. Well, we want every value, right? So we actually want for int value in the row. Want to see out the value. Now I don't want an end line. Did I not use the namespace? Oh, see out. Include IO stream. There we go. When the row is done, then I want to see out an end line. Right? It's not going to be the prettiest board. We're not going to have lines or grids or anything. We could add all that in after if we wanted. I'll probably come back to that because it's going to bother me. Right? But for now, we can get some values back out. Right? We'll at least see some numbers. Okay. All right. It's going to bother me already. So let's start with how about a pipe character? Straight up and down. And before we do all that, we'll see out how about a bunch of dashes here. I think it's 18 of them, or no, 20 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20. I think it's 20. So we'll put one of those between every row as well. So we'll print the row, a pipe, the character, and then another pipe character. And then we'll print that. We'll do every row. Okay, this will probably be a little prettier. They should be able to print the board as a string. Just print it, sorry, print it instead of returning a string. So we haven't finished it yet, but we should be able to give it a board and print the board back out. So over in like main here, if we want to make a board, so a vector of, I got to include vector here, sorry. Let's include vector. My goodness, vector. There we go. Of type vector, of type integer. We'll call this the board as well. Now, I think I can give it these values like this, right? I think we can do this. So we'll give it 5 and 3, 0, 0, 7, 0, 0, 0. Is that 9 values? One more 0. 9 values. Right, and then the next vector, I'm going to do a bunch of zeros here, and then we'll go and fill in these zeros later. So we'll do 9 of these. 3, 4, 5, 6, 7, 8, 9. Okay. So then we have 6, 1, 9, 5, 6, 1, 9, 5. This one here, and then 9, 8, 6. 9, 8, and 6 was here, right? Okay, and then 8, 6, and 3. 8, 6, and is it 3 over here? Okay, and then 4, 8, 3, 1. 4, 8, 3, and was it the last row? Was it 1? Okay, 7, 2, 6. 7, 2, and 6. Right, and then 6, 2, and 8. 6, 2, and 8. and 4195.
You wrote,
Oh, 6, right?
no, that's supposed to be the first one.
First one was the 6. All right, thank you. 4195, 19. Oh, geez, where was it? 5 at the end. All right, and then 879. 8, 7, and 9. Okay, we got our board, right? There we go. So we can make a Sudoku here. Right, Sudoku. Got to include Sudoku. Come on. Include Sudoku. There we go. Let's make a Sudoku given the board. I don't know, Sudoku. Sudoku. Thank you. I'll get this, I promise. It'll work. All right, and then we can call Sudoku.printBoard and get the board back out. Right, we want to see if we can get a board. Right, so let's we'll skip the fib stuff for now, right? See if we can get our board printed out. All of that to print a board. Uh-oh, we did too many end lines, but 20 characters was right. So it's the kind of thing I shouldn't have in my head. Sudoku, so when we're printing here, this last one should be on its own end line. Right, and then the other board here. All right, let's try that. Look at that, that's like halfway pretty here. I know the font's a little small, sorry, I think I can, I clicked on it, it went away. I think we can change the font, but we can print the board out. All right, now we can go back to solve. All right, well, how do we know if we're unique in the row? Right, given a row index. Well, we can return my board, so we want to count of my board.beginning, board.end. Oops, well, what value do we need to check? Well, we probably need to know the value, right, for all of these. If we're going to check for uniqueness, value does not equal 0. Count. What did we do wrong? We had the count before, and it worked. Row begin, row end. Oh, and parentheses. So if the count of that value is 0, right, then it's unique. It's true. Right? If it's not 0, it's false. So a lot of times, and I'll usually make fun of people, but I don't take points off ever, right? They might say, hey, if the count of this is 0, and they would return true. Otherwise, return false. Right? Nothing wrong with this, but it's literally this exact same line. Right? If you're saying if something's true, return true, just return that expression. Right? So don't type more than you need to, unless you're getting paid per line of code. If you're getting paid per line of code, go for it. Right? That's gold right there. Can always make code take up more space. So it's a silly thing people measure sometimes. They're like, how productive are you? How many lines of code do you write in a week? That's a stupid thing to measure, right? Like, it really doesn't tell you anything. Now, like 0 lines of code tells you something, but like 1,000 lines of code versus 15,000 lines of code, I don't know. Is that really meaningful? I mean, I can make a class with like 50 get methods. I've got 150 lines of code there, right? Okay. Anyway, so is unique in the column. This one's a little trickier here, so we just need a loop, right? So we're going to say for int row index is 0, row index is less than my max index, right? We want to use max index anytime we can, or probably the length would be better too, but we know what the max index is here. Row index plus plus. For every row, let's go look. So if my board at the row index dot at the column index is equal to the value, return false. Right? If I found that value at a given row, I'm going to check every row, right? Loop through all the rows, fixed column. If I found that value, return false. If I've looked at every single column and I haven't found it, I can return true. Right? Now, is unique in grid is a little trickier here. This one's a little trickier. Now, looking at this, What we want to do is we want to look at a 3x3 section, right? How do I know which 3x3 section do I want to be in, though? Well, we can do some simple arithmetic. I've done it before. It's not magic, I promise. So I have it in the top of my head because that's the kind of thing that's in my head, right? Okay, we'll do it this way because this is a good way to go about it. If my row is 0, what grid location should I start at, right? Which grid location, right? At 0, right? If my row is 1, here, let's do our table here. So this is the row, and this is the grid, 0. If the row is 1, what grid location are we starting at for that 3x3? Still 0, right? If it's 2, where are we starting? Still 0, right? 3, now we finally moved this row. What row in the grid do I want to start at? I want to start at 3, right? Start at this grid here. So 3 will be a 1, 4 is also a 1, 5 is also a 1, right? 6, now we move on to 2. 7, we move to 2. 8, we move to 2, right? Because now we want to be at this 3x3 grid. Columns work the same way as rows, right? So can I take 0, 1, and 2, turn it into 0, 3, 4, and 5, turn it into 1, 6, 7, and 8, turn it into a 2? You're thinking division by 3, rounded down, right? I knew it. See, I know what's in your head, guys. I got this. Okay, so the int for the starting row index then is going to be my row index divided by 3, right? Integer divided by an integer. Do we automatically round down? Sweet. And then an int for starting column index is my column index, 4 divided by 3. Okay, now for int row index to check. I'm running out of names here, right? Actually, we really don't even need to do anything for that one. We just go, right? We can. It's a little ugly in a for loop, but that's okay, right? Then my starting row index is less than the starting, that plus 3. That's going to be annoying because that one's going to change, right? I guess it can be. I guess we want a new one then. Okay, we'll have a current row index. Starts at the starting row index. We'll go until we hit the current row index is less than the start plus 3. Take the current row index plus plus. All right, I guess that's probably cleaner, right? So we'll have the current row index we're looping through. Start at the starting row. It's either 0. We need to multiply that, don't we? Right? Because that'll be a 0, 1, or 2. So that times 3. Right? Because I need to turn 0 into 0. I need to turn a 1 into a 3, and I need to turn a 2 into a 6 to grab these values. Right? Because I got a 0, a 1, or a 2. Is that right? We okay? It's math. I'm sorry. You guys aren't scared of math, right? You're in calculus. You're done with calculus? Nice. Linear algebra is much more fun than calculus, don't worry. Right, we're going to do the same thing for the column index. Current column index, right, is my current starting column index times 3. Current column index, current column index, current column index. Oh my goodness. Okay, now I've got rows and columns, right? So if my board at the current row index, at the current column index, is equal to the value, we found it here, return false. If after all of that we haven't found it, I can return true. Right? This is why we broke these up into separate steps, right? This is the bigger one here, but you know, if we can place it, it's is the row clear, is the column clear, and is the grid clear? You okay so far? All right, how do we get the first open location? There we go, we're coming back to this now, right? We gotta find the first 0. So I need row index, and then for int column index is 0. Column index is less than my max index. Column index plus plus. Right? If my board dot at row index dot at column index at column index is equal to a 0, we can return row index column index. Oh, sorry, as a pair. I need a pair of int given row index and column index, right? Because we're going to return a pair. Just a cheap way to return two things. I could return it like as a vector, as an array, or all sorts of. But pair is kind of easy here, right? We looked at pairs last week, so might as well use them. Okay. If we go through, we haven't returned anything, right? If it's completely full, I don't know. I could 0, 0. Bad default. I don't know. We aren't doing any sanity checking here, so we'll just assume 0, 0 is probably okay for now if we haven't found an open spot. And it's not going to be able to place any values there. So, all right, so I think we're okay. So let's try now and solve. We got 1 minute left, so hopefully this works, right? Sudoku dot solve and Sudoku dot print. Let's see if it solves. Oh, build errors. Uh-oh. Okay. Oh, my function calls here are wrong. So value, right? Value and value. There we go. How's it run? Nope. What's next? Oh, goodness. Holy cow. None of those are in utility. All right, come on. Where is it here? Where's my error here? You see any red lines? I don't see any red lines. Source? No red lines? Oh, no. Equals standard int. Where am I doing this? Where are my errors? All right, we will finish it on Wednesday then. I'm out of time. Really wanted to finish that, but that's okay. You folks have a good one. I'll see you Wednesday. Where is it not?